Да.
Oh, yes, here
Ага.
we are. Окей.
Ага, я могу тебя объявить уже, да?
Да, да, больше. Говорить надо по-английски, как я понимаю.
So, good evening. We have two speakers with one talk. The first one will be Professor Vladimir Nazaikinskii, and the title of the talk is Exact and Asymptotic Solutions of Systems of Nonlinear Shallow Water Equations in Basins with Gentle Shores. Volodya, you are welcome.
Yeah, thank you very much. So our talk is intended to consist of two parts. The first of which is the nonlinear shallow water equations and all that stuff. And the second is including the reduction to linear shallow water equation in the asymptotic sense. And the second part will concern the asymptotic solutions of linear shallow water equations. The first part will be given by Sergey Dobrokhotov. And the second part by myself. But Sergey is unfortunately in a traffic jam and he will be late, so the talk will begin from the second part. I am sorry if this leads to some difficulties, but I hope not. So we begin with the second part, and this is will be about uniformization and asymptotic solutions of degenerate equations. Well, I will give one example first. So consider some bounded basin with smooth boundary. Where the depth is given by the function d of x. And this basin is filled with water. So this is the domain, say, denoted by omega. And d of x is in C infinity of the closure of omega. D of x is 0 on the boundary of omega. And we will assume that the coasts are shallow so that the gradient of d of x is nowhere 0 on the omega. And the equation we speak about is as follows. The second t derivative of eta is equal to d over dx1 d of x d eta over dx1 plus d over dx2 d of x d eta over dx2 eta at the initial time is equal some eta naught, eta t at the initial time is equal some eta 1. Well, this is basically the Cauchy problem for a wave equation written in divergent form, and this equation degenerates on the boundary. Well, we have boundary degeneration here. Well, and if the initial data looks something like that, you take some point x naught here, a small neighborhood of x naught, and eta 0 is some function v of x minus x naught over h. Eta 1 is, say, 0, and v is a function rapidly decaying at infinity and maybe compactly supported. Is there any problem? No, okay. Well, so if we take an initial data of this form, that t derivative in the initial time is 0, and the function itself is concentrated in a small neighborhood of some point x naught inside the domain, then this is what this equation describes the propagation of a tsunami wave in the linear approximation from the source located at the point x naught. And the problem is to construct the asymptotics of the solution as h tends to 0. But of course, the problem is that our equation degenerates on the boundary. So the usual methods, if there were no degenerations, say, then we could use the standard Maslov canonical operator to get the asymptotics. But here, this is not the case, and we need to do something near the boundary. So this is this example, and I will discuss some more or less general uniformization procedure, which applies in particular to this case. Okay. So about the uniformization procedure. Uniformization procedure. Suppose that we have some manifold M, smooth compact manifold, without boundary. Now suppose G is a compact Lie group that acts on M. And suppose that X, M, but G is the orbit space. The orbit space of this action of G on M. Well, then, on M, we have some structures, some objects. We have the space C infinity of M, of smooth functions of M. We have Sobolev spaces, HS of M, Sobolev spaces. And we have pseudo-differential operators. Say P on the manifold M. Now, in C infinity of M, say, we have the subspace C infinity of M G of G invariant functions. They are invariant on the action of the group G, that they are constant on the orbits of G. And so it is natural to declare that this is what we consider to be the space C infinity of X, the space of infinity differential functions on the orbit space X. In a similar fashion, we have here HS of MG, the subspace of invariant functions in the Sobolev space, and we declare it to be the HS of X in a very natural way. And if we have some pseudo-differential operator P hat, which is G invariant, that is commute with the action of G, then we get some operator H equal to P, say, restricted to C infinity of X. And this will be interpreted as pseudo-differential operator on X. So what I'm saying here is that if we have a smooth compact manifold with a group action, then on the orbit space we can naturally define objects like functions, well-known function spaces, and differential and pseudo-differential operator. Of course, this is a well-known construction. And but now let us reverse the situation. Assume we start from some manifold X, which may have some singularities, and we have some operators on it, and we wish to construct asymptotic or exact solutions for these for equations with these operators. Then we can do the following. We can try to find a manifold M and a group G such that this manifold X is represented as the orbit space, and our operator is represented as the extension of some G invariant operator to the subspace with invariant functions. Then, if we consider, say, the equation H at U is 0, and we are concerned with exact or asymptotic solutions of this equation, okay. So if we have this equation, then to solve it exactly or asymptotically, we should find exact or asymptotic solutions of the equation P hat V is 0. But we are not interested in arbitrary solutions, but only in solutions such that V is G invariant. Well, of course, this is not always possible to represent some manifold and operator in such form. For example, it is well known that if M is a compact manifold and G is a compact Lie group, then the quotient space is always some sort of stratified manifold. So we can only deal with stratified manifolds and not arbitrary, but very special maybe. But nevertheless, this construction proves useful in our situation. And now I will give the very simple example. I guess so. So consider the manifold X, which is just R plus. This is a manifold with boundary, the closed positive half line R plus, and here we have some coordinate X. Well, and assume that we have this equation, the t square, the second derivative of eta is equal to d over the x of x d eta over dx. So this is just the one-dimensional wave equation, which was in the example I begin the lecture with. As usual, when we describe general theory, we speak of compact manifolds, but when we give examples, we just give some model manifolds such as the half line or half space or whatever. This is, of course, not important because we are not very much concerned with the behavior at infinity. We are concerned with what happens near the point zero. So now I will try to represent my manifold as a quotient. So the group will be S1, just the circle. The manifold M, the smooth manifold M, will be R2. I don't know the coordinates by Y. And so I represent the group G acts on M in the usual way by rotations. And I represent X as the quotient space, M over but G, R2 but S1, and well, as a space of orbits, and the projection, say, phi from M to X is as follows. X is the square of Y over 4 This is the projection. So we can think of it as just this. I try to draw R2 in the form of a paraboloid. Well, and this is the projection. What happens then? It turns out that if we take the usual operator, Laplace operator, the usual Laplace operator, then the restriction of this operator to C infinity of x is just d dx x d over dx. So we have this equation, which I, well, what's the matter? This equation, the original equation on R plus, on X, and after lifting it to the manifold M, we have the usual wave equation d2v over dt square is Laplacian V. So non-degenerate wave equation. So by this simple construction helps us to get rid of the boundary. In the beginning, we had a manifold with boundary and equation degenerating on the boundary. And after lifting our equation to M, that is to R2, we obtain an equation on a manifold without boundary. And this equation is no longer degenerate. This is something like that. Well, okay. So in the higher dimensional cases, this is not as good as it is one-dimensional example because some degeneration still remains. But nevertheless, we obtain, as we will see later, equation which is whose spatial part is hypoelliptic in the sense of Radkevich-Aleynik, and so we can prove theorems about these equations, construct asymptotic solutions, and whatever. Okay, what I now wish to speak about is the construction of asymptotics. So let me return from this example to the general situation. So we have this projection. Well, okay, what's the matter? Well, we have this projection. Here we have some equation H is 0, say, and suppose that our uniformization procedure reduces this equation to the equation P hat U is 0, P hat V is 0 on M, and we are interested in constructed G invariant solutions of this equation, G invariant. And I will speak about asymptotic solutions. Also asymptotic solutions. This means that H and P are H pseudo-differential operators. Say in local coordinates, P is P of X minus IHT over dx. Local coordinates. And we wish to construct asymptotic solutions. And to this end, we use Maslov's canonical operator. I mean, M is a smooth manifold without boundary. P hat is an operator with a pseudo-differential operator with without degeneration and with smooth symbol in any way. So why not to use Maslov's canonical operator, well-known tool to construct asymptotics on the manifold M. However, we need to take care that our asymptotic solutions be G invariant, and that's what I will discuss. But first, let me give some reminder about the Maslov canonical operator, because it will be important to us. Well, so we have this manifold M. We have the cotangent bundle of M. And in the cotangent bundle, we have some Lagrangian manifold. And so we have this canonical manifold, and for the Maslov operator to be defined, we need also to have some volume form on this manifold lambda. I will give now some simplified version, assuming that we are given also a volume form on M, which can be fixed by fixing, say, a Riemann structure on M. Well, so if I speak of volume form, then well, I assume that M and lambda are orientable. This is just simplification. General case can also be considered, but don't bother. Well, okay, so if we have these two main geometric objects, Lagrangian manifold and volume form on M, then Maslov's canonical operator, which is denoted by K, and if I need to specify the manifolds, I'll write it like that. It acts from C naught infinity of lambda, from smooth functions compactly supported on the Lagrangian manifold to rapidly oscillating functions. I will write C in H infinity of M, rapidly oscillating functions. These functions depend on the parameter H tending to 0, and they rapidly oscillate as the parameter H becomes small. For example, the simplest case is if lambda is the graph of gradient of some function. Well, then K A can be written in the form of X, A of X divided by the square root of G of X. Well, here it may probably the picture XP. So this is our manifold lambda. Well, and so if we have a function on here on lambda, lambda is diffeomorphically projected on this x-axis, so we can interpret it as a function of x, and this Jacobian is just Gx is dx.
Question. Because square root of Ix, it appeared in your calculation. Can you give me the meaning?
Sorry.
Square root,
I don't.
square root. Who is talking? I don't understand. Okay.
It is me talking.
In canonical operator appears square root of E1. Can you give discussions of this operator?
This canonical. I'm just giving the discussion of the canonical operator.
Oh, sorry.
I'm just discussing it. So this is a reminder. Well, what is a canonical operator? If we are given to define a canonical operator, basically speaking, omitting all details, we need two geometric objects: a Lagrangian manifold in the contingent bundle of M, T star M, and a volume form, the sigma on this Lagrangian manifold. If these manifolds are given, then and some quantization conditions are satisfied in manifold, which I don't discuss for now, but we'll possibly discuss later. Then we have canonical operator defined on this Lagrangian manifold, and it takes functions on the manifold lambda, smooth complexly supported functions. Well, yes, smooth complexly supported functions on lambda. It takes them to rapidly oscillating functions on the manifold M itself. So the simplest example is this. If the Lagrangian manifold is the graph of gradient of some phase function S of X, and is diffeomorphically projected onto the configuration space. This is M, yes. Then the canonical operator gives just these oscillating functions. It is exponential, which rapidly oscillates as h tends to 0. Well, and here we have this amplitude, and it is divided by the square root of the Jacobian. And the Jacobian is in local coordinates. Is the quotient of two volume forms. One is dx1 wedge, etc. wedge dxn, and the other is our volume form, which is defined on lambda. Well, we have agreed that we assume that M is equipped with the volume form, and we only consider local coordinates which are consistent with this volume form. So this form is independent of the coordinates. Coordinate independent. Well, in general case, of course, you have some complications. So your canonical operator acts into half densities, but I will not bother with this. Let's stay at this simple level. And well, if the Lagrangian manifold is not projected on the x-plane, then there are much more complicated expressions involving integrals over some additional variables. I will not go into details here, but instead I will give the two most important properties of the canonical operator, which will be useful for us, and which in fact in some sense describe the canonical operator as a black box. So if you have a pseudo differential operator P, and you act with this operator on T, canonical operator applied to some amplitude A, then it is the same as K applied to this amplitude P. Here it is restricted to the manifold lambda plus O of H. This is the first commutation formula. So if you have your pseudo differential operator P hat is P of X minus IHD over dx, and here we have this function P of X. Well, P, this is the symbol of our operator. Well, and here you have the commutation formula, so you just restrict the symbol to the Lagrangian manifold, multiply by A, and this is the commutation formula, the first commutation formula. So if, more precisely, the symbol usually depends on H, so you have an additional coordinate argument H here, and then we have the principal symbol P naught of XP is P of XP naught. And here, of course, we have P naught in the commutation formula. So if we wish to solve the equation, well, let me write it, P hat U is 0 asymptotically, and we seek U in the form KA for some amplitude A, the first thing we should do is to ensure that this first term in the first commutation formula is 0. So our first wish is that P naught restricted to lambda is 0. That is, we need to construct a Lagrangian manifold which is on the 0 level of our principal symbol, of our Hamiltonian, as they say. Well, but what to do if P naught is 0? Then we have the second commutation formula. P hat of K A is minus IH T of, well, I A plus O of H square, where P is the transport operator, V P naught plus some function F, which is called the sub-principal symbol, and which I have no time to discuss now. Well, and this is the Hamiltonian vector field. This is the second commutation formula. Second commutation formula. And this P is known as the transport operator. This makes sense because if the P naught is 0 on lambda, then the Hamiltonian vector field is tangent to lambda, so this operator is well defined on functions defined on lambda. So when we solve this equation written in red, we first must ensure that we find a manifold lambda on which the principal symbol of our operator is 0, and then we find the amplitude by solving the transport equation, which is the transport equation is PA is 0. Well, okay. So these are two characteristic properties of the canonical operator. And now we will use these properties. So let's return to our problem. We have this G invariant operator P hat. We solve the equation PV is 0. And we try to find an asymptotic solution in the form of some K of lambda d sigma applied to some amplitude A. And we wish to have this function to be G invariant. This function must be G invariant. What is the condition for G invariance? Well, I will assume that my Lie group is not only compact but also connected. So I will for now discard any the action of any discrete groups which can be there, and consider all the connected component of identity. So then the contention of the G invariance is as follows. Let me write it this way. X V is 0 for any X is X of psi, where psi belongs to the Lie algebra of our group. So if we have the action of Lie group on manifold M, then we have the representation of our Lie group. Then we have representation of Lie algebra by vector fields acting in this function space, and so any vector field X in this representation must annihilate this function V. But if we, instead of X, we consider the same vector field multiplied by minus IHX, then, of course, this is a pseudo differential operator, which has some symbol which I write Q of X minus EHD over dx. Well, Q of X pi is a linear function in the cotangent variables pi, and then we need to use our commutation formulas. So for V to be invariant, the first condition is that Q of X pi is equal to 0 on the manifold lambda. Well, if this is the case, well, then how we can interpret this? Our group and has X on the manifold M, and so it also acts by the associated representation on T star M. Well, okay, so this condition, in fact, means that our manifold lambda is invariant under the action of invariant under the G action on T star M. And this condition means lambda lies in the 0 level of the momentum map. Associated with this representation. So this manifold lambda lies in the 0 value of the 0 level of the momentum map, and it is invariant under the action of G. Then we naturally can take this measure, this sigma B, to be G invariant. It is the most natural thing to do, and we can always achieve this by taking an arbitrary measure and then averaging it over the action of the group. Well, and now we apply the second condition, the second commutation formula. Well, then A is constant along the orbits. Constant along the orbits of G. So we have this situation. We have lambda lies on 0 of the momentum map. Well, lambda is in G invariant. Well, and then that amplitude is constant along the orbits. This is also the case, but for now we let us discuss what happens with lambda then. Assume that, so let phi in T star M is with the 0 level of the momentum map, and the phi naught set of weakly regular points. Then we can consider the quotient phi naught, but G is a smooth symplectic manifold. Yeah, this construction is basically none other than the well-known Marsden-Weinstein symplectic reduction. So we can say that this, well, I denoted by phi without the tilde, and we can say that this phi is obtained by symplectic reduction from T star M by the action of G. Note that we have thrown away the irregular points. And the quotient, if lambda is contained in phi tilde naught, then the space of orbits, denoted by L, is a smooth Lagrangian manifold in the space phi. So the basic idea is that the space phi is the adequate phase space for problems on the manifold X, which is M, but G, I recall. And so the correct construction is to construct canonical operator on submanifolds of this on Lagrangian manifolds in this phase space. And the general construction is as follows. For this manifold lambda, we consider the corresponding invariant manifold for this manifold L, I'm sorry, which is in our new space, phase space phi. We consider the invariant manifold lambda. We construct canonical operator on this manifold, and then we only take functions constant along the orbits. And of course, the problem is in specific cases, and also in the general case, to express everything in terms of manifolds X and phi themselves, getting rid as much as possible of mentioning the manifold M in the construction. It is not very convenient to have to say, well, to construct this asymptotic, we just take invariant function of M. Well, the problem is to define them in terms of the manifold X itself. Well, I probably do not have the time to discuss the subsequent constructions in general case in detail, but let me show you in this example how the phase space, what the phase space looks like. Well, okay, so, well, we are again in this situation of X is equal to R plus M is equal to R2. So, and well, let me denote the coordinates on the cotangent bundle by y1, y2, psi1, psi2. Well, then what is the momentum map associated with the action of the group S1 by rotations? Well, the momentum map is just represented by the momentum p phi, which is y1 psi2 minus y2 psi1. So our manifold phi is just phi equals 0, subset of T star M, and this regular part phi naught is as follows. Phi is 0, p phi is 0, but dp phi is not 0. That's the regular part. And so we see that another description would be as well. Okay, how I return to that? Well, okay. So the description will be as follows. Y1 y2 minus xi1 is 0. But at least one of the values y or xi is non-zero. So you see that over the boundary point here, we have very many points of this phi naught, because y may well be equal to 0 as long as xi is not 0. Well, and what is the condition for this? How we can write this phi naught in a different form? We can write it as follows: y is equal to, say, rho times n of phi, and psi is equal to some eta times n of phi, where n of phi is this vector, and rho and eta are just scalar functions whose sum is non-zero. So this is a parametric representation of our phi naught, and the symplectic form restricted to this phi naught is as follows. Is just d eta wedge d rho. So what is the factorization? The factorization is as follows. We need to quotient out the group G, and the group G acts by rotations. That's along the variable phi. So when we take the quotient, we just are left, the variable phi disappears. We are left just with rho and eta. And so we obtain a two-dimensional phase space, which is locally here. The coordinates are rho and eta, and the symplectic form is just as written here. So this construction can be done in this way here, and then we can write the canonical operator and some simplifications which are beyond the scope of this talk, give formulas for the canonical operator, which are show that the canonical operator near this boundary point, in this case, is represented via Bessel functions. So that's why the Bessel functions play so important role in the solutions of the shallow water equations near the shallow coast. Well, that's what I had to speak about in this example. Is my author Dobrokhotov also already here or not yet?
Yeah. Так. Well, thanks a lot. Now we pass the ball to the second.
Yes, exactly.
Thank
you so much.
Thank you. Questions, remarks concerning the first part?
Also know that if you have this space phi is either wanted to be cotangent sort of x. It will always be like that. It's not just locally true, it's globally true.
So my comment is maybe it's
when they this is the maybe a lot of people knows about the works of Alshanetsky and Perelomov when they consider nonlinear equations, but lifted it on the added some additional variable, then obtain linear equation, and then when we pass back, then we obtain the solution, new solution of nonlinear equation. So it's not the same, of course, but it's some analogs of this procedure here.
May I ask you one question, which is related with my questions I asked 2 years ago? Today I understand that the main point of not understanding
Yes.
mine is that I don't know canonical operator method. Am I right?
Yes, I think because you are not, but it is, so the construction, the general construction doesn't connect with a canonical operator. It's just some application of this construction to some, because you can use this construction not only for the asymptotic solution, but to other situations also. But the canonical operator is very useful instrument. Yes.
Very interesting question. I remember that twice I met
Yes,
I met you.
Yeah.
Twice I asked you a question. Once I was the party of Christmas.
Yes.
It was second time it was in Moscow.
Yes.
It was in Steklo. I asked you a question about Fock solution.
Focal point.
In the zero book.
Yes.
This application. That it is evident that solution of this equation is a stone. My question is to you.
Yes.
Do I understand right? And the reason of not understanding is that I don't know manipulator.
Yeah, I think yes.
Thank you very much. Thank you. I'm not sure.
This is the master.
Okay, false.
This is it's a master.
Canonical operator belongs to Maslov. Yes.
But it's long time after Fock.
Yes, long after Fock. But Fock idea was what Fock idea was used is that every canonical classical canonical transform could be lifted to the function from the classic to quantum mechanics, and each canonical transform generate the unitary operator. Yes, and so if you have some singularities in the phase space, for instance, when you projected this Lagrangian manifold to the configuration physical space, then you can make some canonical transform like rotation, and then compensate it in quantum mechanics of wave equations using some unitary operator. If you rotate for P over 2 angle, then it's Fourier transform. But you can use other type of unitary operator and some transform, some canonical transform. So in this case, actually, we start from the Fock quantization of canonical transform, which make compactification of this Lagrangian manifold, because we have singularities on near the beach, near the shore. Yeah, but then we can compactify it, but we use some canonical transform, and to compensate it. Для того, чтобы компенсировать вот это, так сказать, да, что у нас многообразие с особенностью, и это плохо для канонического оператора. Okay, but it is the Lagrangian manifold which we made in this problem near the shore, they're singular. Yes, and that's not singular like in Arnold's sense, because they're the manifolds with singularity, not like the bad projection. Yes, and then we need to do something to complicate this manifolds, but using using some canonical transform. But if we want to compensate it for the wave equation or the shallow water equation, then we need to use something like the unitary operator. Yes, but the more simple way is to lift our problem to the more dimensional space, and then to construct this transformation and so on. And when everything is good and there is smooth, and then come back, and then we lose one dimensional, but then we can solve the problem with the singularities. So this is the idea. Yes. Okay. So я могу.
Я тебе все подключил, экран расшарил, ты вот эту штуку себе нацепил.
Куда?
Главное, чтобы ты это недалеко от подставки.
Как вот вот за эту, да?
Все равно, как все.
Так? I don't know. It is if you have no focal points and caustics, then it is no P.
So it's a very special property. This unitary operator only.
No, but the canonical operator is working.
Let's
Okay,
make a break.
let me.
Proceed after.
Okay.
Да, вот такой.
So, ну что, начинать, да? I can start. So I'm. Just, so Sergey, my name is. Конечно, можно, хотя как.
Сергей мне рассказывал, он мне это рассказывал. Я вот хочу попытаться.
So it's good, видно. Нормально?
Нормально, отлично, видишь, давайте.
Так, ну, so first of all, I apologize that I was late, but it's because but I start 2 hours before talk, but I choose the bad way. I take a taxi, so it's because if I use metro, it will be much better. But I'm a little tired, and so I think, but it's so okay. So, but this is the continuation of our talk with Vladimir Nazaikinskii, but it's actually also some other people participate, and then in particular this Vladimir Klinchenko and Dim Minenkov from our institutes. And so I would like to speak about maybe more simple formulas and more simple objects here. There is no too many geometry, but maybe more differential equation and so on. But I just repeat the problem which we want to solve, and which was reduced to the problem which Vladimir discussed before me. So actually it is the wave equations, the shallow water equations. It is nonlinear equations with a variable coefficient. So there are 3 unknown functions. This is so-called the free elevation function eta, and then the vector velocity. So it is in 2-dimensional. D of x is no more but the bottom. So this is the picture. So there are many applications of this equation. So this the first application is the tsunami wave, and so the tsunami wave could be in mathematical sense, and some approximation could be considered like the Cauchy problem with the localized initial data. This is such this function. And so then we have this small parameter in this problem, and then we can use the asymptotic solution in this situation. So the small parameter is just the ratio between the characteristic size of the source and the characteristic size of the basin. No, for instance, the the wave of tsunami wave, the length of tsunami wave is about 50 or 100 kilometers, and if the basin is several thousands, then it is the parameter is rather small. So then actually this problem is not standard from the mathematical point of view, because we have the problem with the free boundary. So so even if in the open ocean we can linearize it, and the people always do it because the amplitude in an open ocean is very small, so it is like a linear problem. But when we come to the shore, to the beach, then we cannot consider just the linear problem. Shore, берег, берег, beach, shore. And then we need to add this free boundary conditions on the near the shore, and so we have the non-linearity. Even we have special non-linearity. So we have the free boundary. This is the omega. Okay. So now, what is the first step in this case, as I told you before, that is linearization. That is possible to do when we consider the wave in the open ocean. And even if we come to the shore, then we also can use the linearization. But nevertheless, it's not enough to solve the problem. And so the talk of Vladimir was connecting with this problem, which I will discuss a little later. So from the point of view of so we use some geometrical ideas to construct the solution of the linear problem, but it is maybe different story, and it is I have no opportunity to speak about it much, but what we must do, we must solve some ordinary differential system of ordinary differential equation, the Hamiltonian system, and then give us such a pictures like first our solution was localized in the neighborhood of this red point, and then after that we have something like the metamorphosis of the profile of the solution. So first it was like this one localized in the point, and then this is the constant depth. Then instead of this type of solution, we have the solution which localized in the neighborhood of the circle. In the case when we have the variable bottom, like they have some underwater mountain or something like ridge, then we have this type of fronts, and then first it was the front is smooth, then after that it has some singularities, but it is okay. So, but what I would like to say that
this is the picture of the bottom.
This is the picture of bottom. Yes, yes, and that is the propagation of the wave. But by the way, this shallow water equation, it consists not only of the wave part, but also vortex part. And vortex parts also could be considered in our using our method based on the Maslov canonical operator, but modified Maslov canonical operator. And what I would like to say now, just present some simple formulas, effective formulas, which obtained several years ago, maybe 10 years ago, but we used some special tricks, but now we see that actually this formula is no more but a realization of the Maslov canonical operator, but in the special case. What is the special case? The special case is that you know that we have the Vladimir show you that when we use the double VKB representation, then you have the Jacobian in the denominator, the square root of Jacobian. Then Jacobian is equal to 0. It means that you have the focal point. And in this case, which we have in the tsunami wave situation, the Lagrangian manifold is very, very singular. It's like in two-dimensional cases, like the cylinder from in the four-dimensional phase space, which project to the front. So each point on this manifold is a focal one. And so it is then moreover, this manifold is not smooth. And so to use the Maslov canonical operator, we need to modify it, and very strongly. It is our recent work with Vladimir Nazaikinskii and Andrei Shvarevich is published in Izvestia several years ago, 5 years ago. But the result was not only that we can simplify the formulas which are appeared in Maslov canonical operator, classical, but also we can consider more wide class of problems. For instance, this problem is no more but some in the frame of modified Maslov canonical operator. But then what I would like to show you that this is the formula for the this solution in the case, and you see then we have this front, and then if we have no in the regular point of fronts, then we have such the formula for the solution. Just some explanation. What is the formula concept? The x of psi and t is the front of define the front of the solution. Yes, and so locally near some regular point of fronts, we have such a formula, and it consists includes the Jacobian. In this case, it could be factorized, and so you see then what we have. So this is the complete Jacobian here. Yes, but it's factorized, and so we see that it have some divergence in this form because it's two-dimensional case, and that means that it tends to zero. Then many rays comes to the point. So as many more rays, and then it's this function should be smaller and smaller, and this is the bottom D, and so we have some more or less simple representation for the solution. Here we have the function which connect our initial data, like in this problem, with the behavior near the front and here. Yes, and actually this function and so this function localized in the neighborhood of the front. So this is the front x of psi and t. T is time, and psi is just the coordinate on the front. So then it's decay. So this y is the distance between the point of observation and the point of the fronts. But you see, to reconstruct this function f capital near the front, we need to reconstruct it. We need to use the initial data, and this is the formulas for this reconstruction. And the important thing that we have, in general case, we have the integral representation for this formula. It is not the surprise, because we can analyze it from the point of view for the Heisenberg principle, because the solution localized in the neighborhood of the front. So the delta x is small, and then delta p should be, momentum should be big. Big, what does it mean? That's all waves plays role in this representation. What does it mean all momenta? It means that we need to integrate it. Yes, and so this integrate, it is just a reflection of the Heisenberg principle in this problem. But nevertheless, it exists some very important and beautiful example, which was first, it seems, I think that was appeared in the book of Nazaikinskii, first the Russian mathematician and physicist, and he presented in the first edition of this book, and then forget it about it. But what is good, because the Fourier transform of this function is very simple, and then we can construct, then we use
what function?
This one.
What function?
This function at the 0. This is the function. Yes, and then f we can reconstruct in such an algebraic form, and it is very important because we can play with this function, and it is especially now when we have the such programs like Mathematica and MATLAB, and it is important, very important thing, because it plays important role in our home. So So this is examples, and what I would like to stress that actually we have the focal points when this is more or less standard, it is divergence, but the other caustics, it is the shore, the beach, you see, because d equals to 0, it means that we have the caustic. So we can say that the beach is not, or shore is not standard caustics. It is important for the also
Can you say garage another
caustic, caustic.
Нет, вот shore is
Shore берег, берег. Берег это каустика.
берег это каустик.
Берег это каустика, нестандартная каустика. Because this double VKB, some analogs of double VKB representation give the 0 in the denominator. It means that we have the caustic. And so, and this front is caustic, and then the beach, the shore is caustic. So one caustic comes to another one. And so, yes, shore and front also is caustic. So and when I gave a talk on Michael Berry seminar, he said after my talk that caustics are everywhere. So in this case, it's then another interesting example. So is the shallow water in one-dimensional case, and so we have the something like the station in the basins, and so inside of the basin we have the linear problems, but near we have the nonlinear, and but of course linear problem is also not simple because but it was discussed in the part talk of Vladimir. But then even if you construct the linear equation, the solution of linear equation, then it's you need to reconstruct the nonlinear solution because it gives you the splash in Russian Zaplisk and so on. Because without it you have no solution. Yes, it is that. So then another some equation that then you construct also coastal waves is if you have something like the basin like a parabolic bottom, yes, and then near the shore you have some waves which are known like a coastal wave. And so using the ideas which Vladimir discussed, we can construct good asymptotics in this case, and it's connected with the so-called non-standard Liouville tori, because we have the linearized problem has such a classical Hamiltonian, yes, but here you have the you have the shore, this is, and here you have the non-standard caustics again, and you have something like the billiard in this case. This is the standard caustic, like in standard billiard, but this is non-standard caustics, but trajectory reflected the angle of influent waves and reflected waves coincide, but it's as in standard billiard, the angles they are equal.
Billiard has a relation with police, police or no?
No.
Sorry.
Okay. But okay, but the angles always here is P/2. See, that is big difference between the standard billiard and this one. So we called it a billiard with the semi-rigid wells, and then it's possible to construct more complicated case. So now I missed this problem, and I want to now come to the nonlinear situation. So there are some many big literature, but important for us the work of Pilinovsky in nonlinear situation, Pilinovsky and Mazova, and then Carrier and Grespan, and then some other. You can find the complete literature in our published paper here, and then there'll appear also another problems, new one. So, but what I would like to say, when we linearize the problem, yes, then there is no, for linearized problem, there is no standard boundary condition. So you know Dirichlet or Neyman, and it just, you need to, according to Aleynik and Radkevich, you just need to assume that the energy of your solution are bounded. So this is just, that is the big difficult for the numerical analysis. You cannot use the standard numerical analysis, and even if you construct some solution in this two-dimensional case, it is not, you are not sure that you construct the correct solution of your problem, because numerical solution. But you can check it, you can substitute it in the equation and find the small correction. But if you don't use it, there is no this tricks. You see, this is the problem. And now, what is the? I pass on to so the main problems in this case is that the free boundary. Again, I would like to repeat. And now I would like to say that there exists very beautiful trick based on the so-called very simple, which is based on so-called Carrier-Greenspan transform. It is almost nothing necessary to know. You see about it. It is very simple. You see, consider the one-dimensional wave equation, and consider in a case then the depth is a linear function. So this is the curve. And so,
What is the depth?
glubina, the bottom is defined by the linear function. So, and then we can construct, consider this type, for instance, the Cauchy problem, but there exists the Carrier-Greenspan transform. They constructed using this pass into Riemann invariant and so on. But actually, it's not necessary to know anything about it. Just the solution is constructed in such a way. First, we need naive linearization of our original problem, shallow water one-dimensional problem. And then we obtain the one-dimensional linear problem, but with a generated metric here. Like it's equivalent to one-dimensional shallow water equation with the velocity c squared is equal to y. Y, it is the variables in linearized problem. Yes, but but it is possible to reconstruct the solution of our original problem, nonlinear problem, via the solution of this problem, just presenting the solution in a parametric form. So we just make such a transformation. Y and tau is a variable which is naively linearized problem. Then we reconstruct y and tau via t and x, original time and original physical variable. And then if we do it, then we construct the exact solution of this nonlinear problem. So it's just if you know what does it mean, the parametric given function, then you can use this trick. You see, this is it. I don't know, but it's possible. We take it from the paper of Carrier-Greenspan. Also, it was not written in such a simple way. You must do something, yes. But some maybe remark. You see, when you consider this equation, yes, and then it is you see that the shallow water equation it's changing its type. So inside the basin it's a hyperbolic system, but outside it is elliptic. Yes, and of course then you can say, oh, but it is a Tricomi equation. But some simple examples show you that if you construct if you consider you can construct some exact solution of this system which is harmonic in time, yes, and n is the Legendre polynomial. And if you want to use the Tricomi trick to continue your solution outside of the bank, you see that is the absolutely stupid things, because the solution is no the solution of the Tricomi equation, but it's, you need to use the nonlinear situation. Okay, so this is some shallow water, yes. Да, shallow water, yes. But this is some explanation just how to construct the passage from this equation, original equation, to the using the Carrier-Greenspan transform. So this is just a simple equality. Everybody can do it by hand. So this is just an exercise for the second year of the students. So yeah, but then it's possible to construct some solution of such type, but let me miss it. But what is important, that we construct some exact solution. The Carrier-Greenspan, they construct a solution based on the Bessel function of using their tricks, but we construct with Brunel-Perotz many years ago some solution, exact solution, which looks like solitary waves. And how we did it? It is also important because we construct using this source, which I showed you before, for the two-dimensional situation, for the shallow water or for the wave equation. It's the same. You can construct such type of exact solution of this equation. You see, and then what we do, we take this function. Then when you come a little, you go far from, you went far from the source, the source. Then it means that you have quite big x. Then you can say that the front is more or less the straight line, and pass from two-dimensional case approximately to one-dimensional case and construct a solution near this straight line. So just some trick, some linearization of this thing. And then we obtain the solution, the asymptotic of this exact solution in two-dimensional case in this form. Yes, and that is very beautiful fact that this function, if you substitute in the one-dimensional, if you consider the Cauchy problem for the one-dimensional shallow water equation, linear shallow water equation, then you obtain the exact solution in such a form. So this is the exact solution of it is important for our future consideration. You can, using this formula, you can construct many other solutions. You can integrate it, or you can maybe after that you can differentiate it and construct a lot of interesting different solutions of this case. So let me. Yes. Yes. What you see, that is what was solution which we construct first in two-dimensional case. Let us have such a form. Yes, it's like. But if you integrate it, this is something like if you far from, this is solitary wave. Yes, something like solitary wave. But if you integrate it, you can construct something like the shock wave, smooth shock wave. Okay, so let me, maybe it is, but I have no much time. So, but it's interesting case that you can connect the standard. Ой, я забыл. Sloping. Медленно меняешься. Пологая. Gentle, sloping. Gentle, maybe sloping. Преобразование, как он называется, годографа. Yes, it's possible to connect the Carrier-Greenspan transformation with godograph transformation and construct also reduce standard water shallow water equation to this equation with this type of equation. So, but let me use. But what is the important thing? You see. So what is the important thing? So when we construct so maybe come back to Carrier-Greenspan transform. Carrier-Greenspan transform is very simple. Yes, but nevertheless, in practice, it is not sometimes very simple to use it. Why? Because we have not only the free elevation here. Yeah, take a look. Yes, but we have also what this is Carrier-Green-Swan transform. But we have just we must change not only the x, but we must change also t, and it's included. This transform is included includes the velocity. Yes, and this is not very good, you see, because it is some trouble. Yeah, but for and it is one dimensional. Yeah. Yeah, but if you have the solution of the shallow water equation, then it's possible to do. But if you want to generalize it, it is a big trouble, you see. And what we consider when we play with our exact solution, which I show you the formulas, these formulas, yes, we see that if we omit the velocity in Fourier in transform, the Carrier transform, and just restrict ourselves to change of the bottom in such a form, no bottom, but variable x in such a form. Yes, we omit the velocity in this transform. Yes, then the difference between the exact solution, which based on the for this function, which are based on the exact Carrier-Green-Swan transform and modified and simplified, it is almost the same. Moreover, then of course this doesn't work always, because before the breaking, and before the breaking almost complete current transform, and that's modified current this transform, all the same. But this is possible, so this is so y and d, and so we can generalize it in such a case, and it is experimental from this picture.
So it's curious.
Yes, it's curious. Yes, yeah, but we don't. But it was, yes, it was great surprise. Yes. Great surprise for us. Yes, and yeah, but now we can generalize it, because you see, it's not unique generalization, but we can generalize it for the two-dimensional case also, because there is no velocity here. Of course, we must do it just not necessary to do it everywhere, just near the shore of Kulaberiga. And so we put here this cutoff function. Yes, and then this is the sum. And what we construct? We construct the transformation which stop the boundary. Yes, because we have the free boundary. And if we pass from variables x to the variables which connected with the Carrier-Green-Swan transform, we stop the boundary. And then we obtain the problem which was discussed in linear approximation. We obtain the problem which was discussed by Vladimir. Yes, and so this is the so what we want to do. So the D do something like of this transformation of our variables near the shore, and then it allow us to reduce nonlinear problem to linear one. And then
when you say the problem discussed by Vladimir, the case when capital D was replaced by X.
Yeah. And what is the result? You see, the result is that very simple from this point of view, that is nothing necessary. There's no many things people must to know. You see, must know. You see, you just have the original equation, then you have the bottom, and you have such a transformation. So you take what, look, this is the original problem, Cauchy problem, for instance. Then this is the free boundary conditions. Then we assume that the shore described by the smooth function d is this one, and then the gradient is metric sloping bottom. So gradient is not equal to 0. Yes, it means that, for instance, no linear function in the neighborhood. Yes. Then what we must do? First step, we linearize it in naive way. We just omit this linear, non-linear terms. Yes, not this one and this one. And we obtain the linear equations and assume that we construct nonlinear. We construct some exact or maybe asymptotic solution of this linear problem, boundary problem, but without standard boundary condition. Yes, and then if we construct some solution, such type, something solution, then near the shore we can reconstruct the solution of nonlinear equation using these formulas. So this is the linear solutions. Then we pass from the variables y and connected with the linear equation to x, solving.
That you formed, remember you said Kawasaki.
Yeah, but it is we can forget about this. We can forget. We know, of course, and take in our mind that actually the shore. But it's to use this trick is you can forget about it. You see, yes, and it's just because to construct the solution of linear problem, of course, but to pass from nonlinear to linear and from linear to nonlinear, it is not necessary to know about it. Just you need to construct a solution in the form of in parametric form. This is the, and then it's possible to use the approximation method. You construct the solution of this. It's nonlinear equation, yes, but it is not a differential equation. It's just a functional equation, and you can use just the some approximation, and the two approximation give you good result. So and we did it. So and this is the main result of our this part. You see, so first you linearize this equation, and second, after linearization, you construct some solution, and then you can reconstruct the nonlinear solution of nonlinear equation. They are linear using some principle this formula.
Explain.
Yes. It is not exact, yes, but nevertheless, it's approximate solution of nonlinear equation. So what is the ой, сколько еще мне? Ну, минут, 5 так, 10. 5, хорошо, ладно, okay. So what is now the main idea of the proof? So this trick, of course, is possible to do before the breaking, you see, and that it means that the amplitude of our waves are small, you see. Then we can introduce some artificial small parameter and rewrite our original equation in such a form. Yes? Then after that, we can pass to the new. So there's some definition of the solution, exact and asymptotic solution. It means that the function should be satisfied to our original equation modulo some degree of epsilon, and also the domain when we consider our problem should be also satisfied to approximately. This equation should be satisfied in domain approximately. Yes. And then this is some definition, and then okay. But what we do, we pass from the our original variables in the neighborhood of the shore using this analog of Carrier-Greenspan transform, and then we stop first the domain, the boundary of domain stops after that. It fixed after this passage because we use the parametric form of this change in parametric form. Yes, and then we obtain the nonlinear equations with the such a form. Yes, this is change of variables. And then we expand our solution, present as asymptotic series in such a form, and substitute in this equation which we obtain after this transformation. So this equation after this transformation, and then we obtain the system of such type of linear equations with such, and so that is possible to use some. It is possible to use the standard perturbation method, because it's based on the linear equation and homogeneous linear equation. So it's just a standard method. Not standard from the point of view of the perturbation theory, but of course it's not standard from the point of view that our linear problem has singularity on the shore. Yeah. And that is why it is very useful.
Ask you one
Yes.
question. You
Yes.
said me, you said us that the caustics are short.
Yes.
Can you use these can you use these circumstances to explain the idea or not?
No, but when I show you the solution, you see the non-linear equation that they have the singularities and the short. So that is the caustic. But of course, if you don't know, if you know about caustics, no, it is not the obstacle to use the scheme. You see. So what we obtain this type of equations, and so in each step. Of course, F1 and F2 are not, that is just general representation of the system, yes. And so we must construct a solution of this homogeneous system, and that is why it's good to use this trick which the Volodya discussed in this problem. So, because it of course is equation written in such a form are quite simple, but it's not that it's if you work with them, it is not so simple, of course, because it's a singularities and so on. But if you pass to this, make this uniformization and to leave this problem to, then it's a lot of useful estimates works and so on and so on. But I have no time to speak about it. You see, that is why. So, and maybe some applications. So this is the first application. That's a tsunami wave. Yes. So as I told you, so what we must construct? We can construct Lagrangian manifold or fronts, which based on the such type of Hamiltonian system with type Hamiltonian. Then in open shore, open ocean, we move along trajectories. Then sometimes we can make some singularities, caustics. Then the profile can change and so on. But when we can come to the shore, then we use these tricks which Vladimir discussed, and then Carrier-Gnestrand transform. So this is some application, and it is just some pictures of how. But it's in the process, because to application to the real tsunami, it require a lot of some work, additional work in the process. Then another, this I told you about this type of the billiard, yes, and that is consider the bottom which have such a parabolic form. It's round. Right? And then we can construct some solution which have connected with the eigen functions of this operator. It is just harmonic dependence on time here. And then if we construct a solution of this form, then here we use the tricks which Vladimir discussed. Then after that, we can pass from linear to nonlinear case using this modified Carrier-Gnestrand transform and obtain not only the solution of linear, but splash also and so on. And it is so this is Lagrangian manifold which construct appear in this case. So this is the how to construct. This is caustic standard caustics, and here this is non-standard caustic, the shore. Then you take this curve and move around so you have to construct this. Okay, and then it's possible to express it via, as Vladimir told you, via Bessel function in the neighborhood of the shore. It is not standard caustic, and via Airy function here. It's also our tricks which we suggested, and this is some formulas, and that is the pictures. You see, this is different in the different point of the shore. The puncture, I don't know, and the dot lines. It's the linear solution, yeah. And when we reconstruct it via our transformation, you see this is the splash and so on. Not at all. Okay. Now I want to say that it's possible also to use these tricks, of course, for the one-dimensional case, and it is so-called satious. And but interesting, so some motivation that it's satious, one-dimensional satious is appears, for instance, you can find it in Baikal Lake, but so this is motivation. Satious, it is the long waves, which are very long waves, and it's more or less periodic, and then they realize in the whole basin, yes, and you, for instance, in Baikal, you see here waves and you see here waves. It is the same. So they are located in all the basin, yes. So this is the station. And now, so let me, and then we have some experiment in our institute, which can give a comparison of our formulas and our with the experimental data. So it is some vibration table, then it is a basin, and then a basin we can long basin, yes, and then we construct the bottom, and in a parabolic sense, I tell you, and then we can compare the results in this bottom in one. So the mathematical problem could be formulated in such a way, so we can consider first the linear equation with such a bottom, and then we construct the eigenfunction of the linear equations, and then using this Carrier-Greenspan transform modified, yeah, we reconstruct it for linear case, yes. And it's so what we did, we take the parabolic bottom, so like this one, yeah? Yes, and then interesting fact, and if we linearize this one-dimensional equation, shallow water equation, we obtain the spectral problem which have exact solution in the form of the Legendre polynomial. Yeah? And so it is very good to compare the result connected with such type of bottom. It's easy to realize it in our basin, and so Vladimir Klinichenko did it. And so what is the bottom? And so this is the pictures, and then what is the physical mechanism? So we vibrate it, yes, and then we generate some standard wave or Faraday wave, so called. So this is, yes, and then we can compare the theoretical formulas with experimental ones. And this is the fourth mode possible to compare in this case. And so this is the comparison of exact our results and with experiment. The experiment is the dots, and our formulas is a continuous line. So more or less good. So and then it's possible. So. Okay. No, I think so. So this is good.
One big question.
Yes.
May I ask you?
So thank you very much.
Thanks a lot. Questions, remarks? You have a question?
Yes, I have a very big question.
Very
I have, no, I'm sorry for, I'm first time, okay, I'm sorry. My question is about, you know, I'm specialist in the odd-symplectic geometry. And in odd-symplectic geometry, I like to consider half densities. Yeah. And I remember very well that half densities naturally appeared. The book Gimmin Sternberg for me. It was the book where I show the first half density appeared. And every time when I spoke about symplectic manifold, it appeared half density. My question is very general and general. What do you think using your intuition? Is it possible? Of course, my question is very general. And sorry, можно мне по-русски говорить?
Потом переводим.
You understand my question?
That's what you said.
Yes, it is. No, it is half density, but I know that half density appears in odd symplectic geometry. It is part of the life.
Let me answer this question possibly. Well, of course, in various constructions related to symplectic geometry and in particular to Fourier integral operators, one deals with half densities. But there are several equivalent formulations of the same idea. You can deal with Lagrangian manifold and half densities on it, more precisely with sections of Maslow's line bundle. Well, okay. On the other hand, you can choose some volume form on the Lagrangian manifold, and then you need not consider half densities. Instead, you consider functions instead. This is, in fact, a matter of convenience. You have seen that the formula for the canonical operator I have shown at the beginning of the talk in the WKB contained the square root of Jacobian in the denominator. This is just the expression for the half density. So, well, this is how you represent these half densities is a matter of convenience. I believe that as far as actual computations are concerned, it is much more convenient to deal with functions rather than half densities. So you choose a volume form on the Lagrangian manifold, which is invariant under the Hamiltonian vector field, and then you deal with functions. But of course, you can do the same with half densities. It is no problem. Well, there's no problem at all.
It is my idea, just very, maybe it is very sterile here. I think.
Yeah, I guess.
Okay, I'm sorry for this.
Don't be sorry. Ask the question.
No. For me, I think that half densities sometimes appear in mathematics, and every time when they appear, they need to be studied. It is all that I'm saying. It is all I'm saying.
Yeah, but for us.
Yeah, sure. I completely agree with you. So there is no difference at all between others. Well, there are many languages to speak about the same things. That's all.
Да, в том-то и дело, что с одной стороны они появлялись все время в методе канонического оператора, с другой стороны они, естественно, появляются в плотности нечетной симплетической геометрии, это, которая никакого отношения не имеет к этому. Все имеет отношение. Вот мне кажется. Ну да, я думаю, что.
Но симплетический геометр — это главный, так сказать, объект, который здесь используется.
В общем так, я хочу вам задать один вопрос, который я вам задаю уже. Я хочу, чтобы вы мне объяснили, что причина моего непонимания. Сегодня я сформулировал главную задачу, что причина моего непонимания является то, что я не знаю ничего о методе канонического оператора.
Это не вопрос.
Это ответ. Факт, что вы не идете.
Я хочу.
Скорее наоборот бывает, что очень мало народу знает.
Вот я хочу узнать про это. Вы готовы мне помочь?
В смысле, как готов помочь? Я готов вам какие-то прислать.
Нет, готовы, конечно.
Извините.
Это первый докладчик.
Нет, но я могу сказать, что мы, например, читаем, вот последний просто, ну, the last 5 years, we obtain very beautiful things, you see, in canonical operation, realization. For instance, we can present a canonical operator and many problems there, the special function globally. For instance, we can construct it with for instance, such a very far from the mechanical problems, the orthogonal polynomials, for instance. And what Hermitian polynomials are very interesting fact, for instance. We can construct asymptotic which cover the formulas of very well-known formulas of Schleyer-Ratan. An interesting fact that even if we construct asymptotic for n tends to infinity, you can use the formula for n equal to 1, and mistakes it has 2%.
I'm using this on this thing.
It's different tricks, you see, and then I give some lectures in Physical Technical Institute for the students of the third or fourth courses, like a year, so it's not really me.
Давайте сделаем. Я воспользуюсь, я истреблю, я этот недостаток.
Нет, ну, может быть, это уже всем участникам семинара не так интересно ваше. Может, тогда как-то еще. Там еще 15 человек.
Нет, ну,
I'm sorry, those who are in Zoom, do you have questions or remarks?
No, I don't.
Volodya, remarks, questions?
No.
I understand that you don't have questions, but maybe you have some remarks.
No, I don't have any remarks either.
Okay, so thanks a lot
I
to speakers, and thanks a lot to all the participants, and I say goodbye, so we shall proceed private discussion offline.
so thanks a lot also for the attention.
Yeah. Thank you very much for the opportunity
Володя,
to
спасибо
talk here.
тоже. Я далеко не все понял, но было очень интересно.
Спасибо.
This formula.
Вот эти лекции, которые вы сделали, студенты третьего курса.
Ну хорошо, я тогда прощаюсь. Всего доброго.
Мысленно.
Потому что у нас на современный мир все записано.